Well, hi guys. We're going to do improper integrals today, which they're going to be improper because they're going to either be going all the way out to infinity or there's going to be a discontinuity inside what we're trying to integrate, and those are actually very difficult to see. The first one is really easy to see, so we're going to title this here Improper Integrals. Okay, so let's look at the most obvious version. Let's say we wanted to look at the graph of 1 over x squared, just the right hand side. We wanted to take a look at this graph, and let's say we wanted to find the area starting like at 1. And usually what we would do is we would stop somewhere over to the right, 2, 3, 4, 5, but let's just say we wanted to find the area underneath the curve from 1, and let's just say we wanted to keep going all the way out to infinity. And so what we would want to know is this an infinite amount of area, or does this graph approach the x-axis fast enough so that the area becomes negligible and we actually have a finite number for our integral? Now, we are not allowed to do this integral from 1 to infinity of 1 over x squared. What we are not allowed to do is we can't integrate with a discontinuity. So there's a little trick to this. The trick is we are going to say that we're going to stop at some value, some finite value. In the book it uses a b, so I'll use a b as well. And then we're going to evaluate the integral, and then at the end we'll take that value b and we're going to push it all the way out there to infinity with a limit. So we're going to be combining limits and integration. So here is the idea to answer this. We will say we are going to do the limit as b approaches infinity of the integral from 1 to b of 1 over x squared. So we're tricking our integral. We're like, hey, this value b is going to be finite for now. Later on we'll let b go to infinity, but for now, so we can integrate, we're going to let it be b. So we're going to go ahead and answer our integral. Sorry if I sound a little stopped up. Well, it's because I am. Anyway, of course, to integrate this, we've got to go find an antiderivative, and the antiderivative from 1 over x squared is negative 1 over x. And we want to evaluate this between 1 and b. So let's just keep the limit there. Okay, let's plug the top number in, that's negative 1 over b, minus, then plug the bottom number in, negative 1 over 1. Okay, let's clean that up just a little bit. Not doing the limit yet. So I'll have negative 1 over b plus 1. So that's about as far as I can simplify my integral. Now once I've answered my integral, I'm going to let the limit as b approaches infinity. So if I'm going to push b way to the right on the x-axis, that means that this value, negative 1 over b, is going to approach 0. And so since that value approaches 0, that means that this is a finite area. We're going to say that it's 1. We can also say that the area converges to 1. We're going to use that word converge if we get a finite answer. So you might take the integral from 1 to 999, and then the integral from 1 to 9,999, and you can see on your calculator it's getting closer and closer to 1. You can actually, on your calculator, integrate from 1 to infinity. There's an infinity button on, what is it? I think it's Diamond Catalog. And you can actually do that on your calculator, and it will tell you that the value is 1. Okay, so this idea had an infinity in the integral, and when that happens, you must go through this setup like this. Okay, so let's do another example where it's not so obvious and a little trickier. What if I wanted to do the integral from negative 1 to 0 of 1 over x squared? Now that does not look too difficult, but one problem is at 0, if you plug 0 in for x, you're going to get 1 divided by 0, which is undefined. This graph has a vertical asymptote at 0. See, this graph does this little it's like your volcano graph, I guess, is what I usually call it. So this is what it does. So what we're going to do is we want to start here at -1, and we want to find the area under the curve, and you can see it right here. Since that vertical asymptote, this graph goes all the way up to infinity, so I've got basically this hole there. So we want to see, you know, how much area is in here, including all this stuff up here going all the way up. So we're going to do the same thing, and notice this was trickier though, because I've got, you know, and I don't have infinity in my integrand or my integral, but I do have an infinite discontinuity at 0 at one of these endpoints. So the idea here is we're going to stop at some value b, and we'll let b approach 0. So it's the same kind of process. When you integrate, you can't have a discontinuity in the interior anywhere or at the endpoints. So what we're going to do is we're going to let the limit as b approaches 0, but b is going to be approaching 0 from the left-hand side. So we're going to do a little negative sign there. Integral from -1 to b of 1 over x squared. So let's go ahead and go about answering this integral. The limit as b approaches 0 from the left, antiderivative, -1 over x, evaluated between -1 and b. So we'll plug the top number in, -1 over b, and then minus, plug the bottom number in, -1 over -1. Alright, so let's clean this up just a little bit. This will be the limit as b approaches 0 from the left of -1 over b. Those two negatives make a positive, and then -1. So that's what we have. Okay, so let's now evaluate our limit. We're going to let b approach 0 from the left. So they're going to be really small numbers, and they're going to be really small negative numbers. And so let's just, you know, if you plug in like a 0.1 negative, you're going to get a positive value. But what's going to happen is as b approaches 0, this is going to approach -1 over -0, basically, and it's going to go to infinity. So -1 divided by an itty-bitty negative number is going to approach positive infinity. And we are going to get what's called a divergent integral. So here, trying to find all this area is impossible. It actually grows to infinity. So before we went from 1 to infinity and there was a finite area. Now we went from -1 to 0, and there's too much area there. So the integral does what we call diverges. The only other example that I could think of, oh wait, there's an announcement.
Students, may I have your attention please? The time is currently 4:20. All students should be out of the building or in the building with an adult or sponsor. I repeat.
Okay, I had to pause that. I apologize about that. Okay, the only other kind we're going to look at is if we have the discontinuity is in between the numbers. So if I did something like purple, like the integral from -1 to 2 of 1 over x cubed dx. This looks very easy. Doesn't look like there's any problem at all. However, you will need to know that at 0, which happens to be in the interior of this interval, this graph has a vertical asymptote. See, this graph looks something like this. It's a little bit like 1 over x, except it hugs the x-axis a little better. Looks like that, and then it looks like this. Anyway, you could graph it on your calculator. That's what that graph looks like, basically, just without all of the messy stuff. And so at 0, I have this vertical asymptote. So what we have to do is we have to split this up into two different integrals. We're going to split it up across the discontinuity. We'll go from -1 to 0 of 1 over x cubed, and then plus the integral from 0 to 2 of 1 over x cubed dx. Now, this integral again, this first one, this first integral, negative 1 to 0, 1 over x cubed, we can take a look at that by doing the limit as b approaches 0 from the left of the integral from negative 1 to b of 1 over x cubed. And then this other one is going to be the limit as b approaches 0 from the right, from b to 2 of 1 over x cubed. So that's the idea behind that. So you have to check for infinite discontinuities at the interior points as well as at the end points. So those are two different situations where it might not be so obvious. Anyway, we'll practice this tomorrow in class. This probably will require a lot of practice on your part, so make sure you stay focused tomorrow in class, and I'll see you then.